Hi everyone, welcome back. So last time we were talking about ideal gas mixtures. And I kept on saying, okay, here's this method. We can compare our partial pressures to our mole fraction. They're the same so long as we're an ideal gas. But if we're non-ideal gas, like how do we figure out things then? Well, we have various different ways of doing it. The first one is to bring in our compressibility factor. So if you've forgotten what this is simply my deviation from ideal gas behavior. It's the way I can correct it. So if I know, the ideal gas law, it works really well. I just add a little correction factor for each gas. And so if I know what my compressibility factor is for each gas, I can then use their mole fraction and their individual compressibility factor to find an overall compressibility factor for that mixture. Well, how do I find their compressibility factor? Well, you're going to have to calculate it. And so you can do that either using Dalton's law, where you have a particular temperature and a volume for your setup, and you calculate the compressibility factor for each component in the mixture based on that temperature and volume. Or you can use Amagat's law, which is just doing the same thing, but now with temperature and pressure. So which one's better? Dalton's law. It tends to give more accurate results. So if you have to choose one, use Dalton's law. Okay, so I can do this for each individual one. As long as I have enough information, I can solve this problem. However, there's another rule that works fairly well. So what we can do is we can say, hey, yes, let's treat this as if it was a pure substance. As in, air we can treat it a lot of times as a pure substance. It's not technically, it's a mixture, but we've gotten so used to treating it as one cohesive whole that we just deal with it as if it's a pure substance. But for this one right here, it's saying, like, regardless of what you're dealing with, let's just treat it as a pure substance. And it's got these critical properties, P critical and T critical right here. Which, if you're wondering what those are, well, it's simply all my critical properties of the components, the mixture, times their mole fraction, and then I add them together. Or critical temperatures. So once I've done that, I can use something called K's rule. And K's rule is simply saying I can take my critical properties, and I can develop something called a reduced pressure and reduced temperature. As a note, we've already used a subscript R in this course in thermo. So if you're like, wait a second, isn't that relative pressure? Same symbol, even the same letters, but no, this is reduced pressure. This is different. Relative pressure was how you were figuring out the ends of an isentropic process. This one is for us just figuring out the properties of the ideal gas. And so what is it? Well, it's simply the pressure of my mixture over the critical pressure of that mixture that I've calculated. And I do the same thing for the temperature. And then it says go to this figure A15B. Now this is one of those kind of figures that you could find in like an FE manual if you needed to. Just if you want to have a physical copy, if you don't have this textbook. But you should be able to find it online as well, and probably some calculator in Google if you wish to use it. Now I'm going to go ahead and show you what figure A15B looks like, so we can go ahead and see how you would calculate that. And then we're going to do an example right after this where I show it to you. Okay, so here we are in our appendix for our textbook. We go down to figure A15, which is just our Nelson-Obert generalized compressibility charts right here. And did it go far enough? Doesn't look like it. I'm at A18, went too far, okay. They really need to fix that HTML. But here they are. So it all depends on what you know. So in one case, I know I'm just gonna use this one. So I should go pull it up. So in this case, you can see we've got my relative temperature, dang it, my reduced temperature, and I have my reduced pressure right here. And so for each of these values, I can then calculate it. If I know my reduced temperature and my reduced pressure, I can find my compressibility factor. Okay, so second one over here. Here we go. And this is once again relative temperature and relative pressure. You're like, what's the big difference? Why two charts? Look at the numbers for relative pressure here. Goes all the way to 7, starts at 0. And right here, it goes from 0 to 1. This is just really zooming in on that very beginning of this chart. So with this, if you know two values, you can find it. So if I had a reduced pressure of 3, you can see I have trouble with it too. And let's say a reduced temperature of 1.3, I would go over to right here. I would go up until I hit 1.3. and then I would go over until I hit. So that'd be about a compressibility factor of about 0.65. I'm doing my best there, doing it kind of quickly, so if I didn't do it perfectly, forgive me. So with that, you'll be able to calculate compressibility factor. And with your known compressibility factor, you can go ahead and solve your problems. So let's jump back. The last question you might be having is, well, is it accurate? And the answer is, yeah. It's with about 10% over a wide range of temperatures and pressure. So feel comfortable using this. It's a good method. And it's a lot easier than calculating the compressibility factor for each individual component of your mixture. You still got some work you gotta do, but all of this stuff is easy to find, while calculating the compressibility is not necessarily as easy. So that'll be it for this time. Next time we'll jump into an example problem actually using K's rule and comparing the answers we get to the ideal gas law. Thanks for watching. I'll see you all then. Bye-bye.